we're now going to look at some sum formulas, and I'm going to share 4 formulas, and these are basically a formula for constant, for just a k term by itself, a k squared term, and a k cubed term. Okay, so this would be the sum from 1 to n of some constant. So this would be the constant added to itself n times, so you just get c times n. This would be the sum from k equals 1 to n of k. So this would be like 1 plus 2 plus 3 plus 4 plus 5 on up to n. And you get n times n plus 1 all over 2. So this is the formula in the last video that the Gauss, the child prodigy, used to sum up the first 100 natural numbers. Okay? This is the sum of the first n cubes. K equals 1 to n of k cubed. So this would be like 1 squared plus 2 squared plus 3 squared plus 4 squared on up to n squared. And so this is the formula. Not at all obvious. We're not going to worry about deriving it, but it's just n times n plus 1 times 2n plus 1, all divided by 6. And then the sum of the first n, this should be k equals 1 to n, of the first n cubes. So this would be like 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed on up to n cubed. And it's basically n times n plus 1 over 2, all of that squared. So interestingly, it's this formula squared, right? So now let's use it to find this. We want to find the sum of k equals 1 to 100 of this whole thing. So what I'm going to do is I'm going to simplify this and split things apart and try to get it in terms of these formulas. So let's see what we can do here. So this is k equals 1 to 100. And then see this here? I can let's see. Oh, I'm going to cross off one of those. So this would be like 1 here. And this is just 2k, right? Something like that. So then I'm going to distribute that 2k over. And so I'm going to get like 2k squared minus 4k. It would be like that. So now I can split this sum up over the difference, and I can pull out the 2 constant multiples. And when I do that, I get 2 times the sum, k equals 1 to 100 of k squared, minus 4 times the sum of k equals 1 to 100 of just sum of k. Okay, so now if you look here, we have these 2 formulas, and so what I can do here is I can use these formulas up here. Now one thing I didn't stress earlier is notice that all of these sums start at 1 and goes to n. So in order to use these formulas, you got to make sure k starts at 1 and then goes to n. And if it doesn't start at 1, there's ways to adjust it. You can rewrite things a little bit and simplify. But you do, in order to use these formulas, you have to make sure these start at 1, which in this case they do. So for this one, we would get 2 times, this would be 100 times 101 all over 2. And this would be minus 4 times, this would be this one here, 100 times 101. And this would be 201. All over 6. And I think this would be a good one to put in my calculator. So, let's see, where is it? Here it is. Here the 2's cancel out, so I get 100 times 101 minus 4 times 100 times 101 times 201, all divided by 6. I know it's hard to see that, but I'm just putting it in the calculator. Ooh, and I get a negative number. That's not right. What happened here? So oh, no, that'd be okay. Huh. Did I do something wrong? Oh, I see what I did. Well, no, that's okay. Those should all be multiplied by each other. Oh, I know what I did wrong. I know what I did wrong. And I'm going to just let the video go because you can make mistakes. What I did wrong is I switched these two around. These two formulas. This is the x squared term. Okay? So I should have put this in for that, and then this is the k squared term. This is just the k term. Okay? So this should have been this. It should have been 2 times 100, 101, 201, all divided by 6, minus 4 times 100, 101, divided by 2. That's what I did wrong. Okay. So let's try this again. 100 times 101 times 201 divided by 3. I'm canceling that 2 out. Minus 2 times, cancel another 2 out, 100 times 101. And I get this. This is equal to 656,500. So there you go. If you take that sum, this is what you get. Okay, now here's the thing that we really got to practice here, and this is where maybe it gets a little tricky, and that is we're going to do a sum as k equals 1 to n of an expression that involves a k and an n. So this is a sum with respect to k, so we're going to treat n as a constant. Okay, and then we need to simplify. So let's see what we can do here. K equals 1 to n, and I'm going to distribute the 1 over n here, and I'm going to get 1 over n minus, and this is k squared over n squared, so this would be k squared over n cubed when I distribute the 1 over n. And so I get that. And now I need to split this up. I can split the two sums up over the difference. Okay. So now this is a constant. The 1 over n we treat as a constant. Okay? And so what I can do is I can do the constant multiple rule, which is just from 1 over n, it's just the constant times n. So for this one, I would just get the constant, which is 1 over n, that times n. And for this one, I can pull out a 1 over n cubed because the n cubed here is a constant. And, oh, this should be n, I'm sorry, this should have been, and maybe it was, I think that was a slip of the pen. and this is the sum as k goes from 1 to n of k squared. Okay, so this just becomes 1 minus, and now this is 1 over n cubed, and then the k squared term, or the k squared, the sum involving k squared, we can use this formula. If it's 1 to n of k squared, this is the formula. And so I'm going to put that in for this. N times n plus 1 over 2n plus 1 all over 6. So then I get this here. But notice now this sum with respect to k is now all in terms of n. Okay? So now let's simplify this whole expression here. So I get 1 minus 1 over n cubed times n, and then I'm going to FOIL this out. So I get 2n squared plus 3n plus 1 all over 6. Okay, and then I'm going to distribute the n squared. Well, this n could cancel out with one of these here, couldn't it? So I get an n squared here. So then what I could do is I could write this 1 minus, so these cancel out, and then I get just 2n squared plus 3n plus 1, and then this is an n squared, so this is 6n 6n squared. So I would get this expression here. Okay? And then what I could do is if I wanted n to be 10, I could plug 10 in here. If I wanted it to be 100, I could plug 100 in there. If I wanted it to be 1,000, I could plug 1,000 or 1,000,000. And basically I could let the n go to infinity. So if I did the limit as n goes to infinity of this sum, k equals 1 over n, and I'm going to write the original sum up here. That's equal to the limit as n goes to infinity of this, 1 minus 2n squared plus 3n plus 1 all over 6n squared. And you can take the limit of this as it goes to infinity, because this is a rational function with the same degree on the top and bottom. And so the limit as n goes to infinity of this is the ratio of the leading coefficients. So it's minus 2/6, or 1 minus 2/3. 1 minus 1/3, which is equal to 2/3. And so I was able to take as n goes to infinity, I was able to take the limit. And this is actually what this is if I took the function y equals 1 over x squared, and I wanted to find the area, so this is 1 here, from 0 to 1. So I want to find the area under this curve. This is actually the Riemann sum that would give me an expression in terms of if I had n rectangles. So the 1 over n comes from splitting 0 to 1 into n rectangles, and so this is my delta x. And then this is plugging in the right endpoint of each of the rectangles and getting these values. It's plugging it in to 1 minus x squared. See the 1 minus whatever squared? You're plugging the endpoint in for each one of those into the function. And so this would give you the Riemann sum, or the finite sum, that would give you the area under here. And then by letting the limit as n goes to infinity, this is would be the exact area of that. Okay? And that's where we're headed in the next video. We're going to be setting up a Riemann sum like this, and then simplifying and using these sum formulas here in order to get that whole Riemann sum, get rid of the k, get it all in terms of n, and then we're going to be able to take the limit as n goes to infinity, and it's going to converge on a particular value, and that value will be the exact area. So we'll look at that next.